Hey Rock Buds, it's Rock Papa. Hope you guys are doing fantastic today wherever you are. Today we're going to talk about the rocks and geology of Great Smoky Mountains National Park. We'll talk about how Great Smoky Mountains National Park is in the Western Blue Ridge Geologic Province, and we'll show you where the Western Blue Ridge Geologic Province is as it runs up the eastern United States. Then we'll talk about how the rocks of the park were formed as Rodinia rifted back between 750 and 550 million years ago. We'll look at that process, and then we'll go out on the ground and look at the rocks themselves. So stay tuned for that. If this video is helpful to you, please subscribe. And many thanks to you wonderful and most excellent subscribers. Thank you so much. So here we go, the rocks and geology of Great Smoky Mountains National Park. Many of you have visited Great Smoky Mountains National Park, which I consider to be the crown jewel of the park system. Great Smoky Mountains National Park is the most heavily visited national park in the system, and that sounds reasonable since it's nestled kind of midway along the eastern seaboard where a huge population can access it. It is the repository of the largest hunks of old-growth forest in the eastern United States, and its biological diversity is legendary. Hey Rock Buzz, before we go any further, I just can't resist giving you guys a slideshow of some of the photographs that Grammy and I have taken up there over the years, so here we go. I hope you enjoy them. Okie dokie, so let's get started with some geology. Great Smoky Mountains National Park is part of the Western Blue Ridge Geologic Province. On this map it is depicted in the color yellow, and you can see it runs from Alabama all the way up into at least Virginia. And so, what is the Western Blue Ridge Geologic Province? Let's have a look. The Western Blue Ridge Geologic Province is the remnant of the rifted margin of ancient supercontinent Rodinia, which rifted apart between 750 million years ago and about 550 million years ago. Two important rock groups were created during this rifting process. First, huge amounts of basalt lava and rhyolite lava were produced. For example, the Catoctin metabasalt of Virginia and also the Mount Rogers rhyolite of Virginia. This rifting process also produced huge rift basins, also called grabens, that accumulated massive amounts of sediments that eroded off of adjacent high spots. The rift valleys of East Africa are a modern-day example of these rift basins, as is the Dead Sea of Israel. Great Smoky Mountains National Park is the remnants of those Rodinia rift basins after they were folded and faulted and shoved up on the Cambrian rift-to-drift sequence. Hey guys, the Cambrian rift-to-drift sequence is today's valley and ridge, which was originally topped off by limestone, much of which has been eroded away by now. So let's take a picture-by-picture look at how the rocks of Great Smoky Mountains National Park were formed. Here is Rodinia supercontinent, which was brought together about 1 billion years ago, and now it is getting ready to rift apart. Hey guys, with these pictures that I'm about to show you, one thing to remember is that the vertical scale is greatly over-exaggerated and the horizontal scale is greatly under-exaggerated, so keep that in mind while you're looking at these pictures. Here is a side view of the land crust of Rodinia with a hot mantle plume pushing up on the crust and causing splits to occur in the top. Over to the left of this mantle plume or hot spot, you can see that one of those splits has broken through the crust, and that side of the crust has pivoted down to form a rift basin. And a sequence of sediments from coarse to fine, colored pink in this picture, have begun to accumulate in this basin, mostly coming from the horst or high spot on the right. As rifting continues, a new ocean is being created on the right and is expanding. As we already know, rifting creates and enlarges oceans. And also the rift basin formed in the last picture is split in two by a new high spot or horst. Now we have two basins or grabens, and we will call them West Graben and East Graben. You can see that the pink sediments deposited earlier have been split in two by the merging center horst, and additional sediments have been deposited on top of the pink stuff in both East Graben and West Graben. Here are the names of these sediments that will become the rocks of Great Smoky Mountains National Park. The original pink sediments that have been split in two are called the Snowbird group of rocks, and the new deposits in East Graben are called the Great Smoky group of rocks, while the West Graben deposits are called the Walden Creek group of rocks. We'll talk about all these rocks in more detail later and show you nice pictures. Now, all of these rocks taken together are called the Ocoee supergroup, and after they were deposited, the edge of the continent continued to sink, and the Cambrian rift-to-drift sequence, which ended in the Knox limestone, covered them. Hey rock buds, all of the process that we just talked about came to a conclusion by the end of the Cambrian period, about 500 million years ago. After that came the smashing and crashing of three successive mountain building events or orogenies, so let's look at what they did to these rocks. Here is what Great Smoky Mountains National Park rocks look like after the Taconian, Acadian, and Alleghenian orogenies has gotten through with them. The rocks of East Graben had been folded, faulted, and shoved up on top of the rocks of West Graben, along a very important fault called the Greenbrier Fault. In addition, the rocks in both Grabens were shoved west over the Knox limestone, perhaps 200 miles, along a super important fault called the Great Smoky Fault. Hey guys, that important Great Smoky Fault has other names in other parts of the world. In Georgia, it's called the Cartersville Fault, and I'm not sure what it's called up further north, but it runs all up the eastern United States, and it is situated at about the eastern edge of the Valley and Ridge province. This semi-funky picture shows about how things looked right at the very end of the Alleghenian orogeny. The picture represents the massive folding and faulting that had occurred through the three orogenies. You can see the Great Smoky Fault in dark red here and the Greenbrier Fault in green. Rock buds, can you see that orangey line that runs across the bottom of the picture? Well, that represents the present ground surface of Great Smoky Mountains National Park after millions of years of erosion and weathering. And here's another picture of the way the rocks look today. This was created by Scott Southworth and his buddies at the USGS office in Virginia. If you go to the place called the Sinks in Great Smoky Mountains National Park, you can easily see how the rocks have been faulted and upturned. Mute testimony to the power of orogeny. Okay, here is a colorful, simplified, but fairly accurate geology map of how Great Smoky Mountains National Park looks today. Hey guys, can you see the greenish line with the little triangles on it that kind of wiggles its way across the park? That is the Greenbrier Fault, and it separates all the bluish, purplish, and greenish rocks, which are the Great Smoky Group rocks that were deposited in East Graben, from the pinkish, reddish rocks, which were the original sediments that were deposited in the Graben when it was one big Graben. They would be the Snowbird Group of rocks, and the brownish rocks, which are the Walden Creek rocks that were deposited in West Graben. And the yellow line that goes across the top of the picture, and it is outside of the park boundary, is the Great Smoky Fault, which places the Western Blue Ridge rocks on top of the Knox limestone of the Rift to Drift sequence. Oh, and by the way, I forgot to tell you that the park boundary is that thin blue line. And do you see that blue limestone area that's surrounded by the yellow Great Smoky Fault? That's just north of the park boundary, where the rocks that were overlying the limestone have eroded and weathered away, exposing the limestone beneath, and that whole light blue area is Townsend, Tennessee. Okay, a couple more things and we'll move on. Can you find Cherokee, North Carolina, which is in the bottom of the park? Highway 441 comes right through Cherokee and then goes straight into the Smokies and runs right across it from south to north, and then exits the park into Gatlinburg, Tennessee. Hopefully that will get you oriented if you've never been to the park. Hey guys, this next little section where we look at the tables of the rock types and the different rock groups is kind of boring. So you can hang in here with it or skip on over, because rock pictures are coming up. Okay, let's look at those pink Snowbird group of rocks that represent the very first sediments deposited into the Rift Basin. This table shows those rocks with the oldest or first layer of rocks on the bottom. And in a little bit, when we take a driving tour through the park, we'll look at examples of these rocks. Okay, and here are the Great Smoky Group of rocks that were deposited on top of the Snowbird Group in East Graben. And finally, the Walden Creek Group of rocks that were deposited in West Graben on top of the Snowbird Group rocks that were there. Okay, rock buds, now let's take a geologic road tour of Great Smoky Mountains National Park. We will be starting at the Oconaluftee Visitor Center, which is just north of Cherokee, North Carolina, on Highway 441. And here we can find some excellent examples of the long arm quartzite, which is part of the Snowbird Group of rocks. The yellow arrow points to exposures of the long arm quartzite over, I think, probably in or near the Cataloochee section of the park. The long arm quartzite represents beach sands that were deposited in the Graben. This rock makes excellent stone for construction, and many of the park structures are made out of it. Here is the Oconaluftee Ranger Station, built of long arm quartzite. Quite a number of the restroom buildings and the campgrounds in the park are made out of long arm quartzite. Okay, let's head north on 441. About 2.5 miles to Smokemont Campground. At the very end of the campground, you come to the Bradley Fork Trail, and if you hike up the Bradley Fork Trail, probably about a mile, and look carefully, you have to really look carefully, you will find examples of granite and ice rock that represent the ancient basement rock of the Rodinia supercontinent. And on the geomap, you can see that this stuff is exposed inside the Greenbrier Fault, where the rocks of the Great Smoky Group have eroded away. And I believe this rock is the part of that center horse that came up and split the basin into two sub-basins. Here are some examples of that granite gneiss. You can see in these examples that the minerals appear to be kind of smushed down and elongated in the horizontal dimension. That tells us that these rocks have experienced a lot of tectonic pushing and shoving that kind of smushed the minerals flat. By the way, at Rock Buds, all these pictures were taken of rocks in their places in Great Smoky Mountains National Park, and they were not removed, even though I was very tempted. That makes, because it's against the law, that makes them all examples of leverite. That means you leverite there. Okay guys, now we're driving north on 441 from Smokemont up toward Newfound Gap, which is at the top of the ridge. The rocks in this whole stretch of road, which is about 14 or 15 miles, are the Copper Hill formation of the Great Smoky group of rocks. And the table shows that they were the youngest formation of rocks deposited in the group. Metagraywacke is the most common rock that you're going to see along this stretch of the road. It is made of a matrix of siltstone embedded with small fragments of quartz and feldspar. And those fragments of quartz and feldspar are about the size of Honest Abe's ear on a penny. Metagraywacke tells us a couple of things. First of all, that the material washed into these rift basins or grabens very quickly, and the rock sizes were kind of mixed up. You had the finer siltstone with the coarser quartz and feldspar hunks, and the presence of the feldspar hunks tells us that this material did not stay long in its journey from where its erosion site to the basin. Otherwise, the feldspar would have been eroded away. These kind of deposits that wash very quickly into a basin and have the rock fragment sizes mixed up are called turbidite deposits, and they are very characteristic of rift basins. You might also come across some quartz muscovite schist in the Copper Hill formation, and it represents sand and mud that was pretty heavily metamorphosed, becoming schist in the process. Now we have arrived at Newfound Gap at about 5,000 feet elevation. It's the highest spot on Highway 441 through the Smokies. On the geo map, you can see the greenish area that's labeled ZA, and that stands for the Anakeesta Formation. Anakeesta is graphitic and sulfidic slate, and it represents deep, low-oxygen pockets that received very fine, dark mud that was infused with sulfur from volcanic activity associated with the rifting process. Now we're heading west from Newfound Gap on the Clingman's Dome Road to Clingman's Dome, which is the third highest peak east of the Mississippi. A short but steep hike from the parking lot takes you to this cool observation tower. We're still traveling through the Great Smoky group of rocks, but now we've left Copper Hill Formation and are in the Thunderhead Sandstone Formation. This is one of my favorite Great Smoky National Park rocks, and it also is a turbidite deposit where the particle sizes are all mixed up. I really like it because it has these hunks of blue quartz in it that eroded into the basin from the ancient granite gneiss rock on the east side of the basin. And you can see that the hunks of rock embedded in the matrix are about the size of Honest Abe's head on a penny. Hey guys, a couple of things about the Thunderhead Sandstone. First of all, the presence of blue quartz means that the rock that this eroded from had experienced a lot of heavy-duty metamorphism and smashing and crashing. And the second thing is that geologists call this the Thunderhead Sandstone, but it's not the typical sandstone where all the grain sizes are the same. So that's confusing to me, and that's why I call it Thunderhead Turbidite Sandstone, because it's a turbidite deposit. That term, turbidite sandstone, is my personal term. I don't know how many other geologists would like that, but it works for me, and I hope it works for you too. We're back on 441, heading north and downhill, and now we're in Tennessee. On your left, you can see the Chimney Tops, a very popular hiking destination. And the Chimney Tops are also made of this Anakeesta Formation graphitic and sulfidic slate. A few more miles down the hill, we start seeing hundreds of cars parked along the side of the road, and we know we are approaching the Alum Cave Bluff trailhead on the right, probably the most popular trail in the Smokies. The Alum Cave Bluff Trail leads up to the top of Mount LeConte, and once again we are in the Anakeesta graphitic and sulfidic slate formation of the Great Smoky Rock Group. A couple of weeks ago, Grammy and I hiked that trail, and here's some pictures from that adventure. The volcanic activity that imparted the sulfur into the Anakeesta Formation resulted in some interesting compounds in the bluff of Alum Cave Bluffs. About 15 miles north on 441 from Newfound Gap, we arrive at the Sugarlands Visitor Center. This puts us in the Roaring Fork Formation of the Snowbird Group. There's a little nature trail that you can hike that goes behind the visitor center, and you can see the Roaring Fork sandstone. And this sandstone is the typical sandstone where the sand grains are all equigranular, and it's not a turbidite deposit. Get back on 441 heading north toward Gatlinburg for just maybe a half a mile, and look for a pullout on the right where the trailhead for the old Sugarlands Trail is. Hike out this trail for just about a quarter of a mile, and you'll be in the middle of one of my other favorite rock types, the Pigeon Siltstone of the Snowbird Group. I like this rock because it can be a pretty shade of green, a pretty shade of brown, or a pretty shade of gray, and sometimes it has stripes. Remember when we talked about the Greenbrier Fault, where the East Graben rocks were shoved up across the West Graben rocks? The Pigeon Siltstone was the sliding surface between the two graben, and it got sandwiched in between these rocks and was smeared out and metamorphosed into phyllite. And we're going to see that phyllite a little later on. It's called the Metcalf phyllite. But here we have some pictures of the Pigeon Siltstone for you. Now we go back to the Sugarlands Visitor Center, hang a right, and go west toward Elkmont Campground. Here we can look at examples of the Elkmont turbidite sandstone, another rock of the Great Smoky Group. It is similar to the Thunderhead turbidite sandstone, except that the hunks of quartz and feldspar are generally a little smaller. Leaving Elkmont heading west, now we're driving along the lovely little river, and we're going to pass through the Metcalf Bottoms picnic area. Keep going till you get to the place known as the Sinks on the left. In the Sinks parking lot, you can find examples of the Cades turbidite sandstone. It's similar to the other sandstones of the Great Smoky group, but it has no blue quartz in it. Here's some Cade sandstone, and the Meigs Creek trailhead is here at the Sinks parking lot. It's a really nice trail that follows Meigs Creek up into the mountains. Now we're heading west from the Sinks on the Little River Road, and the whole way we'll be passing cliffs of the Metcalf phyllite. And as you guys remember, the Metcalf phyllite is the metamorphic version of the Pigeon siltstone after it got smushed and slid upon by the Great Smoky group of rocks in the Greenbrier Fault. Metcalf phyllite has a sheen to it. That's because as metamorphism proceeds on it, muscovite mica begins to appear. We finally reach the Townsend Y, where the Little River Road intersects with Highway 321, and we exit the park going toward Townsend, Tennessee. We're going to go out there and have a look at some limestone of the Knox group and some of the Walden Creek rocks. As we're driving through Townsend, we're driving on the Knox limestone of the rift to drift sequence because the overlying rocks of the Great Smoky group and the Snowbird group have been weathered and eroded away, exposing the limestone. We drive about 5 miles through Townsend on Highway 321, looking on our right, and then we see some rock outcrops along the Little River. There's a nice parking lot on the right where we can pull in and examine the Knox limestone. The Cambrian rift or drift sequence happened right after Rodinia rifted and the edge of ancient North America was sinking down. The sea rose, that's called a transgression. As the sea rises during a transgression, first you have the sandy beaches at the edge of the sea. Then as the ocean rises, mud from offshore areas and mud flats and the intercoastal waterway comes up and covers the sand. And as the sea continues to rise, if it's a clear, shallow sea, limey mud covers up the mud, and that hardens into limestone. In this particular case, the sandy beaches harden into sandstone, and that is the Chilhowie sandstone, which we'll see a little bit later. Dark mud is hardened into the Conasauga shale and the Rome shale, and the limey mud is hardened into our Knox limestone. Now this is a simplified version, but it gives you the idea. Here's some of that Knox limestone, and as you guys know, you can easily scratch limestone with a knife, and limestone will readily fizz in acid solution. And by the way, this is the same stuff that is in Cades Cove, and that's why Cades Cove was such a rich area for farming. Now we keep going west on Highway 321 until we see a road with a bridge on our right that crosses the Little River. We take that right turn, and then across the bridge we take a left turn. That puts us on the Old Walland Highway. We're now in the Walden Creek group of rocks that were deposited in West Graben. So let's take a look at some of those rocks. Here's a conglomerate that is called the Shields conglomerate, and it tells the story of a river that flowed with power. And here's some limey siltstone with some calcite veins in it. And here are some examples of siltstone of different colors. All these rocks are of the Walden Creek group. Hey guys, hang in with me a little bit longer because we are getting to the end of this. After we look at the Walden Creek rocks, we retrace our steps and go back to Highway 321, hang a right, continuing our way away from the park until we get to the Foothills Parkway, and we go left on the Foothills Parkway, which is west. This takes us along the top of Chilhowie Mountain, where we can get beautiful views of Maryville, Tennessee and surrounding area, and see lots of outcrops of the Chilhowie Formation sandstone. And if we keep going, we'll arrive at the Look Rock parking lot that leads on a trail to the Look Rock Observation Tower, a beautiful place to be. Hey, most excellent rock buds, believe it or not, we're done. Thanks so much for watching, and thanks so much for hanging in here with me. If this was useful, please subscribe. And this is your Rock Papa saying happy rock hunting to my most wonderful rock buds. Papa out.